everyone. In this video, we're going to be looking at one variable inequalities and specifically polynomial and rational inequalities. We're going to start with a really basic quadratic inequality to illustrate the principle. So if we look here at what we have, x plus 4 times x minus 2 is less than 0. Essentially what this is saying is one factor times another factor has to be a negative number. Now, if two values multiplied together give me a negative number, then I know that one of them has to be positive and one of them has to be negative. So that's the principle essentially that we are going to use in order to solve this inequality. But I have to first start by finding critical values because I'm essentially wanting to know, is x plus 4 positive or negative? And is x minus 2 positive or negative? And that all depends on where they are equal to 0. Because on one side of that value, it'll be negative, and on the other side, it'll be positive. So I need my critical values. In other words, I need to solve the equation. When is x plus 4 times x minus 2 equal to 0? Because that will give me boundaries. Now, we already know how to solve this using the zero product principle. If x plus 4 times x minus 2 is equal to 0, then either x plus 4 equals 0 or x minus 2 equals 0. So my critical values here would be when x equals negative 4 or when x equals 2. Now, essentially what we are going to do is a table of signs. So I'm going to say x equaling negative 4, x equaling 2, divides the real numbers into three intervals. Negative 4 and 2 themselves are not solutions to this inequality because negative 4 and negative 2 are where this is equal to 0. I don't want it to be equal to 0. I want it to be less than 0. So these two values are not part of the solution. However, they do provide the boundaries for the solution. So what I'm going to do is I'm going to look at each factor individually. Where is x plus 4 positive or negative? And where is x minus 2 positive or negative? X plus 4 will be negative for any value less than negative 4. At negative 4, it is equal to 0. So on the values of x that are greater than negative 4, x plus 4 is going to be positive. X minus 2 is equal to 0 when x equals 2. So that's its critical value. For any values of x less than 2, x minus 2 will be negative. And for any values of x greater than 2, x minus 2 will be positive. Which means that their overall product, well, in the interval where both of them are negative, the product will be positive. In the interval between negative 4 and 2, that's where we have one positive, one negative. In that interval, the product will be negative. And for any value greater than 2, both of these factors are positive, so the product of them has to be positive. In this instance, we were looking for where is this product less than 0? So this product is less than 0 in between negative 4 and 2. So our solution is that x has to be in the interval between negative 4 and 2, but not inclusive of negative 4 and 2. That's the solution written in interval notation, or we could write it in set notation, x such that negative 4 is less than x is less than 2, and x is a real number. So that's the basic idea here. Those are two different ways of expressing the solution. But my solution is an interval. All right, so that's the basic idea. That principle applies to all polynomial and rational inequalities. We essentially figure out your critical values and look at it factor by factor. So if I now move on to a quadratic inequality that is not factored, well, my first stage in this is finding critical values. For critical values, I need to solve this inequality. Not solving the inequality, that's my overall objective. Solving the associated equation. So in other words, where is this equal to 0? Where is x squared plus 2x minus 3 equal to 0? Those will not be solutions to the inequality, but they provide the limits for the intervals. So factoring this, I get x plus 3 times x minus 1 equals 0, which means my critical values are when x equals -3 or when x equals 1. Again, these are not part of the solution, but they are the boundaries for the intervals. So -3 and 1. Looking at this factor by factor now, x plus 3 will be negative for values that are less than -3 and positive for values that are greater than -3. And x minus 1 will be negative for values that are less than 1 and positive for values that are greater than 1. I put open circles here to indicate that -3 and 1 are not part of my solution. The overall product is going to be positive where both are negative or where both are positive. So the two outside intervals, and negative where we have one of each. In this case, because I'm looking for where is this quadratic expression greater than 0, I'm wanting the two outside intervals. So in this case, x is part of the interval from -infinity to -3, or from 1 to infinity. And this will be the last one where I also express in set notation, just to kind of remind you of the different ways we can represent our answers. X is less than -3, or x is greater than 1, and x is an element of the real numbers. In this case, because they are two separate intervals, I should see two separate intervals in my answer, either through the two bracketed intervals in the interval notation, or two separate inequalities, x less than -3, x greater than 1 in my set notation. Now, I'm going to just quickly indicate, and I could also just test this out to see if it works. So in other words, if I pick a value from each of those intervals and test it in the original inequality, does it work? So if I pick a number less than -3, let's say -10. So if x equals -10, well, then I have -10 squared plus 2 times -10 minus 3, which is 100 minus 20, so 80 minus 3, 77. That is, in fact, greater than 0. So that works. If I pick a number in between -3 and 1, so for example, if x equals 0, then I have 0 squared plus 2 times 0 minus 3, which is -3, which is not greater than 0. So that's what I was expecting. And if x is greater than 1, so for example, x equals 5, you could pick any number greater than 1. You could even just pick 1.001 if you wanted, although that's harder to calculate. Then I have 5 squared plus 2 times 5 minus 3. So 25 plus 10, 35 minus 3 is 32, which once again, greater than 0, which is as expected. So I can, in addition, or I guess as an alternate to doing the table of signs, once I know my boundary points, so the critical values are a critical piece of this question. Once I know that my three intervals are less than -3, between -3 and 1, or greater than 1, I find the sign table quicker because I don't have to actually calculate anything. But alternatively, you could pick a value that is in each of those intervals and test to see if it works or not. All right, so let's look at a couple more. This one, we actually have two ways to solve it, basically to find our critical values. So if what I'm doing is I'm finding my critical values, you can factor this. Factor out the 3, factor the difference of squares that results. But basically, I'm just solving the equation 3x squared minus 12 equals 0. So if I just want to find critical values here, then I can just move the 12 over, divide by 3, take the square root. I'm not going to do that because I want the factors. I want the factors for my table of signs. So yes, I can solve this equation without factoring, but in the end, I do want the factors. So I'm going to go ahead and factor it. So I get 3 times x squared minus 4, which is 3 times x plus 2x minus 2. which means my critical values are when x equals positive or negative 2. So now that I have my critical values and the factors, I can go to the table of signs. So my number line is divided by negative 2 and 2. Now that's 3. The 3 is technically still part of this inequality. Because it's positive, I don't really need to worry about it. If it were negative, I definitely would. So just as a practice, I always include the coefficient. I'm going to include the 3, the x plus 2, and the x minus 2. The 3 is positive everywhere, so it doesn't affect the sign of the overall answer. But if it were a negative 3, then it would, so I would need to include that negative. So x plus 2 is negative if x is less than negative 2, and positive if it's greater than negative 2. And x minus 2 is negative if x is less than 2, and positive if it's greater than 2. So the overall product is going to be positive, negative, positive. That's often the pattern you'll see, but not 100% of the time, so it's worth checking. And in this case, because I wanted to know when this 3x squared minus 12 was less than or equal to 0, in this case, the minus 2 and the 2 are actually included in my answer. So I'm including the interval where it's negative, so between negative 2 and 2. But negative 2 and 2 are also included in the answer. So x is in the interval from negative 2 to 2, where they are included. The alternate solution to this inequality now, I can solve the inequality just by isolating x, but you have to be very careful with that. So 3x squared minus 12 is less than or equal to 0. 3x squared is less than or equal to 12. X squared is less than or equal to 4 when I divide by 3. Now you have to be careful if you divide by a negative number, because if I divide by a negative number, I have to flip that inequality. And now, when I take the square root, I cannot write x is less than or equal to positive or negative 2. That's nonsensical. That is not the way that taking the square root works, really. We sort of cheat a little most of the time, because really it's not that the square root of 4 is positive or negative 2. It's that the square root of x squared is actually the absolute value of x. So when I'm taking the square root here, what I'm really getting is that the absolute value of x is less than or equal to positive 2. That is another way of expressing this particular solution. Because if the square root of x is less than or equal to 2, it means that x is between negative 2 and positive 2. These are equivalent expressions. So that's another way of solving this type of inequality. All right, so let's move on. We're going to compare these two, which are very, very close to being the same, but something a little different happens with each of them. So in this case, x squared plus 2x plus 1 is less than 0 or less than or equal to 0. The difference between the less than and the less than or equal to is whether I include my critical values in the solution or not. So in the case on the left, the critical values are not going to be included in the solution, and on the right, they are. But what happens when I factor this, so critical values in both of them are going to be the same, because what I'm doing is I'm solving the equation x squared plus 2x plus 1 equals 0. But when I factor x squared plus 2x plus 1, I get x plus 1 squared equals 0. So I actually only have one critical value, and that's when x equals negative 1. For both of these, I can use the same table of signs. So my only critical value is negative 1. Negative 1 may or may not be included, depending on which of these I'm solving. But in this case, my factor, well, it's x plus 1 squared. So because I'm squaring it, it's always positive. If it's always positive, then it is never less than 0. Never less than 0. It is, however, potentially equal to 0. So on the left-hand side, there are no solutions, because the only possibility for that quadratic, x squared plus 2x plus 1, it can equal 0 if x equals negative 1. It can be positive, but it can never be negative. Whereas on the right-hand side, if I say that x squared plus 2x plus 1 is less than or equal to 0, well, it's never less than, but it can equal 0. So in that case, x equals -1 is the only solution. So it's possible, as we saw in the first several examples, and what you'll see most of the time is your solution is going to be an interval or several intervals. So it's a solution set. It is, however, possible to have no solutions, and it is possible to have a finite number of solutions like we have here, just x equals -1. So be really careful about whether that is included or not. It makes a big difference here. All right, let's move on to something other than just quadratic, cubic here. Well, we have to start in the same way. Critical value are when 2x cubed plus x squared equals 4x plus 2. Now, in this case, it is possible to factor by grouping, but I am going to follow proper protocol, move everything over to one side. So 2x cubed plus x squared minus 4x minus 2 equals 0. And that's because when I'm solving this inequality, I actually need to be solving the inequality 2x cubed plus x squared minus 4x minus 2 is greater than or equal to 0. Because this is based on how do I know if a product is positive or negative. So 0 has to be the boundary. It always has to be relative to 0. So I definitely want it there. And I want all the factors. So this one I can factor by grouping, or you can use the strategies we learned for factoring polynomials of higher degree than 2. But factor by grouping is a little easier here. X squared times 2x plus 1 minus 2 times 2x plus 1 equals 0. So 2x plus 1 times x squared minus 2 equals 0, which means that I have critical values at x equals -1/2 and x equals positive or negative root 2. These are included in my solution because I have a greater than or equal to sign. So table of signs, I've got negative root 2, -1/2, positive root 2, obviously not drawn to scale. And now I have, I can think of this as two factors or three. So I'm just going to use 2. I'm going to use 2x plus 1 and x squared minus 2. So 2x plus 1, x squared minus 2. You could use x plus square root of 2, x minus square root of 2. That also works. And these solutions are all included in my answer because I have greater than or equal to. 2x plus 1 is going to be negative for values less than -1/2, positive on the other side. X squared minus 2, now it has two critical values, negative root 2 and positive root 2. What I'm just going to do here is I'm just going to sort of think through a test value in each interval. So smaller than negative root 2, let's say -5. -5 squared is 25, 25 minus 2 is positive. Between negative root 2 and -1, well, -1. -1 squared is 1, 1 minus 2 is negative. Between -1/2 and root 2, 0. 0 squared minus 2 is negative. And greater than root 2, 10. 10 squared minus 2 is positive. So the overall product in each interval, I've got a negative, a positive, a negative, a positive. I want the ones where it is positive because I want to be greater than or equal to 0. So that means that my solution, x, is an element of the interval from negative root 2 to -1/2, inclusive of those boundary points, or root 2 to infinity. Infinity is never included, but all the other ones are. So there we have it. Now, rationals, same idea, but now we have to bring in also the idea of non-permissible values. Our non-permissible values are critical values, just like the others. So to find critical values, I'm going to solve the associated equality. So x squared plus 3x minus 40 over 2x squared minus 18 equals 0. So I've got the factors in the numerator, x plus 8, x minus 5. and the factors in the denominator 2 times x plus 3 times x minus 3, equaling 0. Now this is equal to 0. A fraction is equal to 0 if the numerator is equal to 0. So I've got x equals -8 or x equals 5. These are going to be included in my solution because I have greater than or equal to 0. But I also have my non-permissible values. X cannot equal -3. X cannot equal 3. These are also critical values because they can never be 0, but that determines on one side of it whether it's positive or negative. So in other words, my table of signs needs to include all of these values and all of these factors. So I have critical values at -8. That one is included in my solution. -3. -3 cannot be included in my solution one way or the other because x can't be that. I've got 3, which also cannot be included in my solution. And I've got 5, which is included in the solution. So you have to be careful with rationals because some of your critical values may be included and some can't be included. For factors, I'm actually going to look at 5 different things. I've got x plus 8. I've got x minus 5. I've got 2. I've got x plus 3. And I've got x minus 3. Now, you don't technically have to include the 2, but I always do include the coefficient because if it is a negative number, you definitely have to include it. So now, for x plus 8, it's negative if it's less than -8 and positive for all the others. X minus 5 is negative for x less than 5 and positive for greater. 2 is positive everywhere. X plus 3 is negative if we're less than -3 and positive if we're greater than -3. And x minus 3 is negative if it's less than 3 and positive if it's greater. So now, my overall sign for product and quotient, multiplying and dividing, depends on the overall balance of positives to negatives. So basically, if I have a negative times a negative, divided by a positive, divided by a negative, divided by a negative, it's an even number of negatives, so they all basically cancel each other out. So overall, I have a positive. Between -8 and -3, I have a negative. Positive between -3 and 3, negative between 3 and 5, and positive for greater than 5. I'm looking for the ones that are greater than or equal to 0. So the intervals where the overall fraction is positive. So I actually have 3 intervals here. So x is an element of the interval from -infinity to -8, where the -8 is included, or -3 to 3, they are not included, or 5 to infinity, where the 5 is included. So rationals kind of add a little level of complexity on it, but the overall idea is the same. We're looking at all the factors and where are they positive or negative in order to figure out if the overall expression is positive or negative. Let's do another one of those. So this time, I don't have it compared to 0. I have it compared to 2. Can't have that. Has to be relative to 0. So I have to start by moving that over. So x minus 3 over x minus 4 minus 2 is less than 0. But that minus 2 isn't helpful. I need this expressed as factors. So I actually need to simplify this fraction first. So I need to get that to a single fraction. So that's what I need to be looking at, is a single fraction being compared to 0. So in order to do that, I need a common denominator, which in this case is just x minus 4. So I've got x minus 3 minus 2 times x minus 4 over x minus 4 is less than 0. When I simplify that, so I get x minus 3 minus 2x plus 8. So we have 5 minus x over x minus 4 is less than 0. So my critical values here, I don't need to factor anything because they're just linear. So my critical value, well, the numerator will equal 0 when x equals 5. And my non-permissible value, x cannot equal 4. So those are my intervals. I've got 4, which can't be included, And I've got 5, which also isn't included because I just have less than, not less than or equal to. 5 minus x is my first factor, and x minus 4. Now be careful when you have a subtraction in a backwards order than what we normally see. So 5 minus x is actually going to be positive if x is less than 5 and negative if it's greater. And x minus 4 is negative if we're less than 4 and positive if it's greater. So we end up with negatives on the outside and a positive in the middle. We are looking for the negative intervals because I have less than 0. So the two outside intervals, which means that x is an element of the interval from negative infinity to 4, not inclusive, and 5 to infinity, also not inclusive. All right, so that takes practice. Feel free to go back over those examples a little bit, but the basic principle is the same for all of them. So it's lesson 9.2 in your textbook. There's a worksheet on polynomial and rational inequalities in D2L, and the worksheet that you got actually quite some time ago with rationals has questions 16 and 17 that are about rational inequalities.